Okay, so let's look at an example of the map, say H from R2C to R2C given, oh, let's do something really simple. So what I want you to do is go through the process. See if you can, let's go through the process. We don't have that much time left. Let's go through the process of showing that this map is both linear, checking all those properties. Linear, one-to-one, and onto. Okay? Check or verify. Okay, so what we do to show that this map is linear? Well, we'd have to look at f of, well, let's use the other. If I we have to, well, okay, we have, here's an arbitrary linear combination, and we'd have to choose two vectors for arbitrary R and S. We'd choose two vectors. We want to choose um, R of x1, y1 plus S times x2, y2. Okay, and then we would check F, and we'd combine this into moving, this would be Rx1 plus Ry1. Then we'd add it to Sx2 plus y2. Now we have it in a form that we can apply this to, where it just flips the order. So this is going to be Ry1 plus Sy2, Rx1 plus Sx2. And just like we did last time, we want to, oh, yes, y1, y2, x1. We have the ones on this side, the y. So we can actually pretty simplify this as now r times y1, x1 plus s times y2, x2. And we can see that this is r times f of v1, because this is the image. If I put ones here, it just flips the image, plus s times f of v2. So therefore, since I've called this, again, I somehow be stuck on the letters F, H, H, H. Okay, so therefore, H is linear. Okay, and then we want to, let's say we check one-to-oneness. Well, how do we check one-to-oneness? We have to check that if the image is the same, if the image is the same, the original vector is the same. So we'd have to check, well, one-to-one means that if H of V1 equals H of V2 for any V1 and V2, then V1 equals V2. So we'd suppose that this one, V1, if V1 is this vector here, x1, y1, then we'd suppose that y1, x1 equals y2, x2. But then right away, we'd see the two equations are y1 equals y2 and x1 equals x2. So right away, this implies that v1 equals v2 and h is 1-to-1. Then to check that it's onto, we'd have to say, okay, given and say uh, let's do it this way. Let's say you have a PQ and we want to find we want to solve, given PQ, we want to find an X and a Y that leads to it. Okay. So, well, right away, um, no, that equals F of XY. So what we would do is we would say, here, we'd say for any P and Q, this is any element in the codomain, any codomain element, then you have to find a YZ. What you're doing is you're choosing any P and Q and then saying this has to equal this. Well, that means, not YZ, sorry about that, X, YX, because this is the image that you get from here, from H. And it's clear that I have to solve this for P and Q so I can choose that X equals Q and Y equals P. So for any Q and P, I found the X and the Y that will um, wait, yeah, Y equals P and X equals Q. So this mean therefore H is onto. Maybe this is a little bit seems like sleight of hand because it's so simple. But the point is you can sort of see directly from this map that it's just switching X and Y. So it's going to be onto because I can get if I choose any numbers X and Y here, I can just reverse them and find the vector that came from it. And it's 1-to-1 because if I choose any vector here, it's going to go to a different vector here. If I choose 1, 1 here, it's going to go to 1, 1. I can't choose some different numbers that also go to 1, 1. And then it's also linear. So you can see that the three with the simple map, you just have to sort of keep straight what the goal is. Okay, so therefore H is an isomorphism because we verified that it's linear, therefore it's a linear map and it's 1-to-1 and onto and linear. Okay.